Good morning, students. Today I'm going to cover a topic on multi-degree freedom vibration system by using matrix method. In my previous lecture, I discussed about analysis of multi-degree freedom vibration system by writing equation of motion and subsequently writing that in matrix format. In this method, we would calculate the frequency of multi-degree freedom vibration system along with the mode shape of the same vibration system. This is being done by calculating eigenvalues and eigenvector. So what I'm going to cover in this is we'll discuss about matrix method equation. What is the governing equation for matrix method? Then we will learn how to calculate eigenvalue and eigenvector and their application in calculation of n natural frequencies of n degree of freedom vibration system, and then I'll explain it through example problem. So let us take one n degree freedom system. Now we know that for any vibration system we can write the equation of motion of the combined n degree freedom system by using this matrix, that is m x double dot plus k x, where x double dot represents the acceleration of mass 1, mass 2 up to n. Similarly, x represents the displacement of mass 1 to n in the matrix format. So the governing equation in the matrix format for n degree freedom system can be given by this equation. Now what I do is that I simplify this equation by multiplying m inverse on both the sides. So the equation can be written as m inverse m x double dot m inverse k x. Now if any matrix, this is mass matrix, so represents the mass of different n masses into the system. So if it is multiplied with the inverse of this, that results into unit matrix. So m inverse into m can be written as unit matrix multiplied by x double dot plus this new term where inverse of m and k stiffness matrix, multiplication of both is written as a new matrix, that is C, and multiplied by x is equal to 0. So this becomes the equation number 2. Now the important thing here is, because whenever we want to calculate the value of C or the value of C in matrix form, we have to calculate first the value of mass matrix inverse and multiply it with the stiffness matrix. So you must know how to calculate the inverse of any matrix, which you have already studied in your mathematics course. But to give you an idea, the matrix inverse can be calculated as equal to adjunct of the matrix divided by determinant of that matrix. I'll show you how to calculate this inverse by taking one example. Now we know that we have already written an equation of motion in the matrix format. So we have to propose the solution of that equation of motion, and that solution of equation of motion is also written in the form of matrix, that is x is equal to capital X sine omega t. Here one thing I would like to explain through this that once you have written equation of motion that is in the form of m x double dot plus kx, so k x is equal to 0. So the solution, this is x double dot. So the solution of this equation can be given as x in the matrix form, x is equal to capital X that represents the displacement, capital X, and sine omega t, omega t, where this x element is capital X represents the displacement of n masses x1, x2 till xn. And this is one matrix, and this x represents the displacement solution x1, x2, and till xn is equal to sine omega t. Okay, so this is how we propose the solution for the given matrix. Now you have to calculate, because you need to put this value of solution to the governing equation, that is the equation of motion. So you have to calculate the double differential of this equation for the solution. So x double dot would be calculated as minus omega square x sine omega t. Now assuming omega square is equal to lambda, so I can write minus lambda x sine omega t, where omega is square is equal to taken as lambda. Now putting these values of x double dot in the governing equation of motion x double dot and the value of x from the solution, your equation comes out to be minus lambda I x sine omega t plus c x sine omega t. This is obtained simply by putting the value of x double dot here and x here and multiplying both the sides by m inverse. So you are putting the value of x double dot in this equation number 2 and the value of x here. So you get the equation as minus lambda I x sine omega t c x sine omega t. I repeat again. So the solution which you are proposing here, you would calculate x double dot, and the value of this solution is being put in equation number 2, x double dot and x, and you get the equation in this format. Sine omega t is common, so it is going to be cancelled out. So the equation becomes equal to c minus lambda I, and x is taken common, so c minus lambda I is equal to 0. I can write this equation since I have not written here. So I'll write this equation becomes equal to c minus lambda I, where I is unit matrix, and multiplied by x is equal to 0. So this is the equation which you obtained as a governing equation for in the matrix format for the n degree of freedom vibration system. Okay, where lambda represents what? Lambda represents omega square, or the ith natural frequency can be calculated by taking square root of lambda I. This lambda represents the natural frequency and is called as eigenvalue. And when you put the value of lambda in this equation, you will get the value of x for different masses, that is called mode shape, and the way of calculating mode shape is called as eigenvector. Let me take one problem example and try to explain how to develop this or how to solve by using a matrix method. So suppose there are 3 degree of freedom system where masses are connected with the help of a spring having stiffness K, K and 2K, where the masses are M, M and 2N. So first of all, what I will do is that I'll draw the free body diagram of individual mass, mass 2, mass 3, and then I'll write subsequently the equation of motion for each mass. I'll write the equation of motion in such a way that they are in terms of coefficients of x1, x2 and x3. So let me explain this through mass M1. It is connected through the 2 springs, one upper spring having stiffness K and lower spring stiffness K. So this mass is displaced by an amount x1 that would lead to stretching of the upper spring and compression of this spring, assuming that x1 is greater than x2. So there would be a net compression of this spring. So when a spring is stretched, that exert a force on the mass on the upward side. So the force exerted by the spring on the mass would be K into displacement of this mass, that is x1. Similarly, the force exerted by, since this is under compression, so it is going to exert a force on upward direction on this mass. So the force exerted by the spring on this mass would be K, that is stiffness of this spring, multiplied by the net displacement, so that is x1 minus x2. So and this is an acceleration force which is m into x1 double dot. So from the equation of motion we know that acceleration force is equal to net force applied on the mass. So mx1 double dot is equal to, since the direction of this acceleration is downward, so all the forces which are acting in downward direction are taken positive and else are taken negative. So this force is acting in upward direction, so it's taken as negative minus kx1, and this force is acting upward direction, so it is also taken as negative, so minus kx1 minus x2. Simplifying this equation would give you the value, or would give you the equation of motion as mx1 double dot plus 2kx1 minus kx2 is equal to 0. So you can solve this equation, you will get this equation of motion for mass 1. Similarly, you will get equation of motion by drawing the free body diagram for mass 2. you will get the equation of motion as mx2 double dot 3k x2 minus k x1 minus 2k x3. Similarly, for mass 3, since there is only one spring, this is under compression because x2 is more than x3, so this is going to be under compression. The net displacement of this spring would be x2 minus x1, x3, and that would be under compression. So the force exerted by this spring on the third mass would be downside, and that is equal to stiffness, that is 2k multiplied by net displacement, that is equal to x2 minus x3. So the net force coming on to this mass is downward direction with the value 2k multiplied by x2 minus x3. And this mass is also undergoing some acceleration. So 2m x3 double dot would be the acceleration force acting in downward direction. So writing equation of motion for this mass would be acceleration force, that is 2m x3 double dot, is equal to net force acting onto this mass, that is again acting in the downward direction or in the same direction as acceleration force is acting. So it is taken positive, that is equal to 2k x2 minus x3. Solving this equation, you can write the equation of motion for third mass. So in this way, you can write the equation of motion for all three masses. Now I'll rearrange all these equations in such a way that I'll get the equations in terms of coefficient of x1, x2, and x3. Okay, so rearranging these equations, I'll write this equation in terms of, first I'll write coefficient of x1, then x2. Similarly, I'll write this equation in terms of x2, x2, x1, x3. Similarly, I'll write this equation x3 double dot x3 minus 2k x2 multiple coefficient of x2 is equal to 0. Okay. Now, what I will do is I'll prepare the mass matrix and the stiffness matrix of out of these equations. Okay. So here you know that in the first equation of motion for mass m, there is only one mass which is multiplied with x1 double dot. So coefficient of x1 double dot would only be with mass m. And in this equation, x2 double dot coefficient is 0, and similarly x3 double dot coefficient is 0. So what I will do is that I'll write the mass matrix for this equation as m0, 0. Similarly, for the second equation of motion, I'll write the mass matrix for second equation, since coefficient of x1 double dot is 0, coefficient of x2 double dot is m, and coefficient of x3 double dot is 0 in this equation. So I'll write the mass matrix as 0, m, 0. Similarly here, in the third equation, we will see that the equation has got only coefficient of x3 double dot, whereas x1 double dot coefficient and x2 double dot coefficient are 0. So the mass matrix for this would be 0, 0 to m. Okay, so writing all these coefficients of x1 double dot, x2 double dot, and x3 double dot in the cumulative mass matrix, for the first equation it is only x1 double dot coefficient is there, so it is m0, 0. x2 double dot coefficient is 0, x3 double dot coefficient is 0 in equation 1. Similarly, for equation number 2, x1 double dot coefficient is 0, so I have written here 0. x2 double dot coefficient is m, so I have written here m. x3 double dot coefficient is 0, so I have written here 0. Similarly, for third equation, I can write this as 0, 0 to m. Let me then write down the stiffness matrix. The stiffness matrix is again written with the help of coefficients of x1, x2, x3. So x1 coefficient in equation 1 is 2k, x2 coefficient is minus k, and x3 coefficient is 0. So I'll write 2k minus k 0. So 2k minus k 0 for equation 1. For equation number 2, you would find the coefficient of x1 is minus k, coefficient of x2 is 3k, and coefficient of x3 is minus 2k. So I'll write minus k, 3k, and 2k. So minus k, 3k, 2k. This represents the coefficient of x1. This represents the coefficient of x2. This represents the coefficient of x3. Similarly, for mass 3, the coefficients of x1, x2, x3 in terms of stiffness are written like here. So you have prepared out of the equation of motion the mass matrix and the stiffness matrix. Now we have to apply this equation which we have earlier derived in order to find out the natural frequencies by calculating the value of lambda. Okay. Now here you need to calculate the value of C. So C we have already discussed is nothing but multiplication of inverse of mass matrix multiplied by K. Now the important thing is here is to calculate the inverse of any matrix. So inverse of this matrix is calculated by calculating adjunct of mass matrix divided by determinant of matrix. So first of all, you must know how to calculate the determinant of this mass matrix. Now to calculate the determinant of that mass matrix, what you will do is that you would calculate it by element wise. So from first element, striking off this row, corresponding row and column, you would multiply the remaining terms, that is m multiplied by 2m, that is positive, and multiplication of these two terms could be taken negative. So this m element is multiplied with 2m square minus 0 here. Then second element, so corresponding row, corresponding column, and corresponding row are striked off. So remaining element are 0, 2m, 0, 0. So 0 multiplied with 0 minus 0. Then let us calculate it, the third value, by striking off corresponding column of third element and row, and the remaining element are 0, 0, 0m. So it is 0, 0 minus 0. So the total value of this determinant comes out to be 2n cube. Then once you have calculated the value of m, you have to calculate the adjunct of matrix M. Now, adjunct of matrix is to be calculated by following certain steps. What are those steps? The first step is to calculate the minor of each element of mass matrix. Okay, so for each element, you have to strike off the corresponding row and the column and multiply the two elements, that is 2m square multiplied by minus of this value. So this value comes out to be 2m square. This becomes the minor of m. Similarly, you go for the next element, multiply the two elements, that comes out to be 0. So this becomes the minor of element 0. Then you go for the third element, the remaining here is 0m 0, 0. So this value comes out to be 0. Similarly, the next element, corresponding row and corresponding column is to be striked off. So 4 elements remaining. These two elements are positive multiplication. These two elements are negative multiplication. So value comes out to be 0. So for each element, you have to calculate the minor values. Now those minor values has to be placed in place of that element. So 2m square has to be placed here with respect to m. 0 has to be placed here. This minor has to be placed with respect to this. This minor has to be placed here. This minor has to be placed here. This minor has to be placed here. Similarly, you get the minor of matrix M. Once you have calculated the minor of matrix M, then you have to calculate the matrix of cofactors. Cofactor matrix can be calculated by multiplying the minor of matrix of minors with this sign convention: plus minus plus minus plus minus plus minus plus. So this 2m square is multiplied with 2m plus, and this is taken negative, this is taken positive. Similarly, this is taken negative, this is taken positive, and you get to another matrix that is called matrix of cofactor. Then the next is to calculate adjugate by interchanging of diagonals. So you have to, from this matrix of cofactors, you have to interchange the diagonals. So this diagonal, this forms a diagonal, this 0 forms a diagonal with this 0 forms with diagonal of this. These elements have to be interchanged. So this becomes adjugate. Now you have calculated the adjugate of matrix M, and you have calculated the determinant of the matrix M. So putting those values here, you calculate the M inverse value. So multiplied inside, you will get the inverse of this mass matrix as 1 by M 0 0, 0 1 by M 0, 0 0 1 by 2M. Now the value of C is calculated as multiplication of M inverse and K matrix, stiffness matrix. So this can be done simply by using the principle of matrix multiplication, and you get this value. That is the value of C. Now putting the value of C in the equation, governing equation, which is C minus lambda into I is equal to 0. So you get the eigenvector as putting the value of C here, which is calculated from here, and lambda multiplied with unit matrix, it is this. Okay. So solving this would give you the equation a matrix is equal to 0. Now you have to solve this matrix. That would give rise to, you have to solve this first again in the same way. First element is corresponding row and column are striked off, and multiplication of these two columns, two elements with positive sign, and multiplication with negative sign. Okay. Similarly, for the next element, you have to multiply. So in the same way, you have to calculate this value. So the equation after simplification comes out to be this one. Point here is that this equation is in terms of cubic equation in terms of lambda. That represents that it is going to have 3 roots. So 3 degree of freedom vibration system would have 3 natural frequencies. So if you solve this equation, you get the value of lambda 1 as 0.139 k by m, lambda 2 as 1.746 k by m, and lambda 3 is equal to 4.115 k by m. These values are called eigenvalues. From the eigenvalues, you can calculate omega 1 because you know that omega square is equal to lambda. So omega 1 is equal to square root of lambda 1. You calculate the 3 natural frequencies through the eigenvalues. Now putting the values of these lambda in this equation, putting the values of lambda in this equation, you will get the values of mode shape, and that this equation is called as eigenvector. Okay, so from the matrix method, you can calculate the natural frequency of n degree of freedom system through eigenvalues, and you calculate the mode shape by calculating eigenvector. But both the things have to be calculated separately. So this method becomes slightly complex when number of degree of system, freedom of system increases. So what we are going to do is that in the next lecture, we are going to discuss more simplified method to deal with n degree of freedom vibration system, that is called method of influence coefficients. And in that way, we would learn how we can calculate the influence coefficients in order to calculate the natural frequency and the mode shape of any n degree of freedom vibration system simultaneously. So this influence coefficient method would help us calculate natural frequency and mode shape simultaneously, whereas in this method, we have to calculate, matrix method, we have to calculate both natural frequencies and mode shapes separately. Okay, students, then in next lecture, I'll come up with a new method that is called influence coefficient method, and we'll discuss the underlying principle of influence coefficient method, and we will take one example in order to understand the methodology of solving a problem using influence coefficient method. Okay, thank you very much.